This is Food Chemistry Unit 2, Chapter 20, Thermal Preservation, Hot and Cold Processing. Thermal preservation is changing the temperature or heat energy of a food. Most foods can be preserved by adding or removing heat energy. The goal of any food preservation is to improve shelf life, and shelf life is the time a food can be stored and still safe to eat. So first we'll look at heat processing. This transfers heat energy into a food. Now heat denatures enzymes, which are proteins, and destroys microorganisms. These are two of the main causes of food spoilage and contamination. Heating alone will not extend shelf life. It needs to be packaged to prevent contamination. Degrees of preservation. Blanching. This is suspending food in boiling water or steam for a short period. It denatures enzymes that can cause loss of flavor, color, or texture. Fruits and vegetables are prepared this way for freezing. It loosens the skin for easier peeling on such foods as tomatoes, peaches, and apricots, for example. Pasteurization. Foods are heated at low temperatures to preserve foods by eliminating pathogens and extending shelf life. It destroys pathogens and denatures enzymes. Beer, wine, fruit juices, milk, oysters, and eggs are pasteurized. Pasteurized eggs provide a great substitute for raw eggs in dishes served in schools and nursing homes. All right, sterilization. Commercial sterilization is a heat preservation for canned foods in sealed containers. All microbes that cause illness, produce toxins, or spoil foods are destroyed. Most of your canned foods will last 1 to 2 years. Any longer and the quality of the food changes, but the microorganisms should not grow. Sterilization in general is a complete destruction of all microorganisms. So all parts of the food reach 121 degrees Celsius for 15 minutes in the presence of water. Why water? It's a better conductor of heat than air. Variables affecting the method of heat transfer. You have conduction. So this would be for products where the food does not move in the can, like your corned beef hash, pumpkin pie filling, and tomato paste. These are thick solids in here. So heat is transferred by molecular collisions from outside to inside of the can. Convection. Heating sets up currents in a liquid. So liquids in the bottom of the can can be heated by conduction. Currents set up a stirring motion, right? And that speeds up heat transfer to the rest of the can. So these would be your cans that hold liquids, like chicken broth or juice. Now, conduction and convection together would be for foods that have solids and liquids in the can, like a fruit cocktail. Liquids are heated by convection, and solids rely on conduction to transfer heat to the center of the chunk of food. Food irradiation. Food can be exposed to high-energy electromagnetic waves. This is a type of pasteurization. It was typically used for sterilizing medical equipment, cosmetics, and wine bottle corks. There was a move toward food, things like bagged and loose spinach and iceberg lettuce. The technique can protect large volumes of food from insects, mold, and sprouting. In 1963, the first foods irradiated were wheat and wheat flour. Irradiation protects food from, let's go by food. Wheat, it protects it from insects and mold. Potatoes from rapid sprouting. Spices and herbs, it lowers the risk of contaminants. In pork, it destroys trichinella. Fruits and vegetables can be protected from mold and insect damage. Poultry, it can destroy salmonella. And in red meat, it can destroy E. coli. Now, what are the effects of radiation on food products? Well, there can be chemical changes. Irradiation forms ions in foods, also known as free radicals. Free radicals cause changes that result in the death of microbes, and it blocks some reactions like sprouting or ripening. Free radicals are also formed during digestion, cooking, storage, and freeze drying. So it's not just from irradiation. There's more free radicals in a piece of toast than in irradiated food, just saying. Radiolytic products are formed from irradiation, such as CO2, that's carbon dioxide, formic acid, and glucose. These are also commonly found in many foods. Since these products, though, are then added into the food, irradiation is a food additive, but it does not alter the nutrient content of most foods. Not every food is meant for irradiation, so sprouts or fish eaten raw like oysters cannot undergo this process. It would damage the food itself too much, and it would not taste the same. The energy used to irradiate foods could be gamma rays, electron beams, ultraviolet, or X-rays. This is pretty powerful energy. Gamma is the strongest and would require radioactive elements. Electron beams are machines that are more expensive, but they don't use radioactivity. UV, that's ultraviolet, would be only for surface treatments. And then X-rays would be for your thicker foods and shipping containers, which are, it's hard to focus the X-ray. All right, so there are public concerns about irradiation. So let's take a look at these. Will eating irradiated foods increase the risk of genetic damage to humans? No. Is irradiated food radioactive? No. It does not decrease the risk of botulism, but it does reduce salmonella and E. coli. That tells you how tough botulism, the bacteria that causes that is. It's very, 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 very strong, very tough. There's concern with how radioactive chemicals are shipped or if they will melt down. So far there are no accidents that have occurred in shipping, and the amount of material is too small to melt down like a reactor. So I do understand these fears, but there really is no greater risk. It just sounds like it's more dangerous, but it's not.